What secrets truly lie on the side we've never witnessed from our home planet? What unimaginable discoveries await us there, in a place only robotic probes and intrepid astronauts have glimpsed? This is not just a tale of scientific exploration, but an odyssey into the unknown, a quest to unlock lunar mysteries that could reshape not only our understanding of the cosmos, but also humanity's very future. The implications are profound, paradigm-shifting, touching upon everything from the origins of our solar system to the very possibility of sustained human presence beyond Earth. If you're ready to peel back the veil and uncover these lunar mysteries with us, then like and subscribe right now, and let's begin this incredible adventure.
For millennia, humanity has gazed upon the moon, a familiar face in the night sky. Its waxing and waning a constant companion, its craters and seas a source of endless fascination. But what if I told you that this familiar sphere holds a profound secret, an entire half that has remained perpetually hidden from our view? This is the story of the moon's far side, an enigmatic realm that, for most of human history, existed only in our imaginations. It's a story woven with threads of scientific discovery, engineering marvels, and the enduring human spirit of exploration. We'll delve into the astonishing geological differences that set this hidden hemisphere apart, explore the tantalizing potential for resources like water ice and helium-3, and ponder the dramatic implications these discoveries hold for the future of lunar exploration and beyond. This isn't just about rocks and dust, it's about our destiny among the stars. We'll break down complex astronomical and geological terms, making them accessible to beginners, while providing enough detail to captivate seasoned astronomy enthusiasts. Prepare to have your perceptions of Earth's silent guardian forever altered.
For eons, the moon presented only one face to Earth, a celestial sentinel locked in a perpetual dance. This phenomenon, known as tidal locking, is a cornerstone of our lunar relationship. Imagine a delicate gravitational tug-of-war between Earth and its moon. Over billions of years, Earth's immense gravitational pull acted as a cosmic brake, slowing the moon's rotation until its rotational period precisely matched its orbital period around Earth. This means the moon completes one rotation on its axis in roughly the same time it takes to orbit Earth once, approximately 27.3 Earth days. The result? The same lunar face, pockmarked with familiar Maria and craters, always greets us. This alignment is so precise, so enduring, that until the dawn of the space age, no human eye had ever directly observed the moon's opposite face. It was a blank canvas, a tabula rasa upon which humanity projected its wildest dreams and deepest fears. Was it a mirror image of the side we knew, or something entirely alien? The mystery deepened with every passing century, fueling speculation and inspiring generations of scientists and dreamers. The very notion of a dark side, though inaccurate in terms of sunlight, as both sides experience day and night, took root in our collective consciousness, implying something hidden, unknown, perhaps even sinister. Then, on October 7, 1959, the Soviet Union achieved a monumental feat that forever changed our understanding of our celestial neighbor. The Luna 3 probe, a marvel of early space engineering, swung around the moon and captured the very first images of its enigmatic far side. The world held its breath. When those grainy black and white photographs were finally transmitted back to Earth, they unveiled a landscape dramatically different from the familiar face. Soviet scientists, huddled around flickering screens, reportedly gasped in astonishment. Gone were the vast, dark plains of solidified lava, the Maria, Latin for seas, that dominate the Earth-facing side. Instead, Luna 3 revealed a heavily cratered, rugged terrain,
an ancient, battered surface seemingly untouched by the widespread volcanic activity that shaped the near side. It was a cosmic revelation, a testament to human ingenuity and a stark reminder of how much remained to be discovered. This initial glimpse was more than just a scientific achievement, it was a cultural earthquake, shattering millennia of assumptions about our moon and opening up entirely new avenues of inquiry.
The visual starkness between the lunar near and far sides isn't merely aesthetic. It's a profound geological puzzle that has captivated planetary scientists for decades. While the near side boasts expansive dark maria like the Sea of Tranquility where Apollo 11 landed, the far side is conspicuously lacking in these features. Instead, it's a mosaic of ancient, heavily cratered highlands, often appearing brighter due to their composition. This dominance of highlands is a key characteristic, suggesting a very different evolutionary path for this hidden hemisphere. The term anorthosite, a light-colored feldspar-rich rock, is frequently associated with these ancient highlands. It's thought to be a primary component of the moon's primordial crust, the original shell that solidified after the moon's formation. The sheer prevalence of anorthosite on the far side points to a crust that is considerably thicker than that of the near side. This thicker crust, some theories propose, may have acted as an insulating blanket, preventing molten material from easily reaching the surface to form vast volcanic plains. It's like comparing a thin, easily punctured membrane to a thick, impenetrable shield. The reasons behind this dramatic crustal asymmetry are still debated, but leading hypotheses center on the moon's formation and its early chaotic history. One prominent theory, an extension of the giant impact hypothesis that explains the moon's very existence, suggests that Earth played a crucial role. As the newly formed moon orbited a still hot Earth, the intense thermal radiation from our planet may have preferentially heated and thinned the near-side crust, while the far side, shielded from this heat, remained cooler and thicker. Another intriguing idea involves a double impact scenario, where a second, smaller, moon-like body, formed from the same colossal impact that created our moon, eventually collided with the far side. This slapdash impact, as some scientists jokingly refer to it, could have deposited an extra layer of material, adding to the far side's crustal thickness and explaining its lack of maria. Regardless of the precise mechanism, the resulting geological dichotomy presents a natural laboratory for studying planetary evolution, offering tantalizing clues about the moon's turbulent past and, by extension, the early history of our own solar system. The difference is so stark, it's almost as if we're looking at two entirely different celestial bodies fused together. What grand forces, what cataclysmic events sculpted such disparate landscapes on a single world? This fundamental asymmetry continues to be a driving force behind our fascination with the moon's hidden face.
Among the far side's most striking features, one truly stands out, not just for its immense scale, but for its profound scientific implications. The South Pole Aitken Basin, or SPA Basin. This colossal impact structure, stretching approximately 2,500 kilometers, or 1,550 miles in diameter, and reaching depths of up to 13 kilometers, or 8 miles, is one of the largest and oldest impact basins in the entire solar system. To put that into perspective, it's roughly the size of the contiguous United States, deep enough to swallow Mount Everest several times over. Formed billions of years ago during the moon's early bombardment phase, the SPA Basin is a monumental scar, a testament to the violent cosmic ballet that shaped our planetary neighborhood. Its sheer size suggests an impactor of truly staggering proportions, a rogue asteroid or protoplanet that delivered a blow of unimaginable energy, excavating vast quantities of lunar crust and potentially even exposing material from the moon's mantle. This makes the SPA Basin a geological goldmine, a window into the moon's deep interior. Scientists believe that studying the composition of the basin floor could provide unprecedented insights
into the moon's internal structure and its primordial composition. Imagine a giant natural drill hole bored by a cosmic projectile, offering us a direct look at what lies beneath the lunar surface. Missions like China's Chang'e 4, which landed within the SPA basin in 2019, have already begun to explore this incredible region, analyzing its unique mineralogy and searching for clues about its formation. The basin's rim is also a fascinating area, with towering peaks and deep shadows that hold another tantalizing secret: water ice. Because of the extreme angles of the sun's rays at the lunar poles and the depth of the basin, many areas within the SPA remain in perpetual shadow. These permanently shadowed regions, or PSRs, act as cold traps, preserving water molecules from solar winds and sublimation. This trapped water ice, a precious resource, could be crucial for future lunar missions and even long-term human settlements. The SPA basin, therefore, is not just a relic of the past, it is a potential wellspring for humanity's future in space, a place where ancient history meets future potential. What secrets of the early solar system, what vital resources for our future does this colossal scar truly hold? The journey into its depths is just beginning.
The notion of water on the moon once seemed like science fiction. For decades, it was widely believed that our natural satellite was utterly bone dry, a desiccated wasteland incapable of supporting any form of life or sustained human activity. But then came a series of groundbreaking discoveries, starting with the Clementine mission in the 1990s and dramatically reinforced by LC-CROSS, Lunar Crater Observation and Sensing Satellite, in 2009. These missions, along with data from India's Chandrayaan-1, provided compelling evidence for the presence of water ice, particularly within the permanently shadowed regions, PSRs, of the lunar poles, and especially within the deep craters of the South Pole Aitken Basin. These PSRs are akin to cosmic freezers, where temperatures plunge to extraordinarily low levels, sometimes as cold as -240 degrees Celsius, -400 degrees Fahrenheit. At such frigid temperatures, water molecules, delivered by comets and asteroids or formed by interactions between solar wind protons and lunar soil, remain frozen, protected from the sun's intense radiation. The implications of this discovery are nothing short of revolutionary. Water is the key to sustainable lunar exploration and colonization. It can be melted for drinking, sustaining human life. It can be purified for use in life support systems, allowing breathable air to be generated. Most crucially, water can be split into its constituent elements, hydrogen and oxygen, through a process called electrolysis. Hydrogen and oxygen are the fundamental components of rocket fuel. Imagine, instead of launching all the fuel from Earth at immense cost, future lunar missions could refuel directly on the moon, using resources extracted from its poles. This transforms the moon from a mere stepping stone to a genuine staging post for deeper space exploration, a cosmic gas station for voyages to Mars and beyond. The hidden hemisphere, once thought barren, now gleams with the promise of a self-sufficient future. How will this abundant water fundamentally alter the economics and feasibility of our journey into the cosmos? The potential is truly staggering, a game changer for humanity's expansion into the solar system.
Beyond water ice, another resource on the moon's hidden hemisphere has captivated scientists and futurists alike: helium-3. This rare isotope of helium is incredibly scarce on Earth, but it is relatively abundant in the lunar regolith, the loose, dusty layer covering the moon's surface. Unlike its more common sibling, helium-4, helium-3 is a non-radioactive isotope with enormous potential as a fuel for nuclear fusion reactions. Fusion is the process that powers the sun, where light atomic nuclei combine to form heavier ones, releasing vast amounts of energy. On Earth, scientists are racing to develop fusion reactors using isotopes of hydrogen, deuterium, and tritium. But these reactions produce radioactive byproducts. Helium-3 fusion, however, is unneutronic, meaning it produces very few neutrons and thus minimal radioactive waste. This makes it an incredibly clean energy source, a holy grail for future power generation. The Moon's regolith contains significant quantities of helium-3, deposited over billions of years by the solar wind, which constantly bombards the lunar surface. Because Earth's magnetic field largely deflects the solar wind, helium-3 doesn't accumulate here in the same way. Estimates suggest that there could be millions of tons of helium-3 embedded in the Moon's soil, particularly in the upper few meters. The challenge, of course, lies in its extraction. Helium-3 is not present in concentrated veins. It's diffused throughout the regolith. Mining it would involve heating vast quantities of lunar soil to extremely high temperatures to release the gas, a monumental engineering undertaking. Furthermore, the economic viability of transporting helium-3 back to Earth for fusion reactors is a complex equation, dependent on the future development and widespread adoption of fusion power. Despite these hurdles, the promise of clean, virtually limitless energy from a lunar source fuels intense interest. Could the Moon's far side become the ultimate power plant for a future Earth, a silent cosmic battery powering our civilization for millennia? The prospect is tantalizing, a vision of abundance born from the lunar frontier.
For much of the space age, lunar exploration was dominated by the United States and the Soviet Union. However, in the 21st century, China has emerged as a formidable force, particularly in its focus on the Moon's hidden hemisphere. The Chang'e program represents a new era of lunar exploration, pushing the boundaries of what is possible. The most significant achievement to date came on January 3, 2019, with the historic landing of Chang'e 4 in the South Pole Aitken Basin. This marked the first ever soft landing on the Moon's far side, a technical marvel that overcame immense communication challenges. Because the far side is perpetually out of direct line of sight with Earth, direct communication is impossible. To overcome this, China deployed a dedicated relay satellite, Kuiqiao Magpie Bridge, positioned at the Earth-Moon L2 Lagrange point, a gravitationally stable location beyond the Moon. Kuiqiao acts as a crucial communication link, relaying signals between Earth and the Chang'e 4 lander and its rover, Yutu-2. The Yutu-2 rover, still active years after its initial landing, has traversed hundreds of meters across the far side's rugged terrain, providing unprecedented data on its geological composition. It has utilized its advanced instruments, including a ground-penetrating radar, to probe beneath the surface, revealing insights into the structure of the regolith and the underlying layers. The mission has confirmed the presence of unique minerals and provided further evidence supporting the hypothesis of a thicker far-side crust. Beyond the scientific data, Chang'e 4's success has immense symbolic significance. It demonstrated the capability for sustained operations on the hidden hemisphere, paving the way for future, more ambitious missions. It has also spurred other space agencies to reevaluate their lunar strategies, intensifying the global race back to the Moon. What other secrets will Yutu-2 uncover as it continues its methodical exploration of this ancient alien landscape? The robotic pioneers are charting a course into a truly unknown frontier, revealing the Moon's deepest mysteries 1 centimeter at a time.
One of the most compelling reasons to establish a human presence or scientific observatories on the Moon's far side is its unparalleled potential as a radio quiet zone. Earth, with its bustling human activity, is a cacophony of radio signals. Everything from cell phones and Wi-Fi to television broadcasts and military radar emits radio waves, creating a pervasive electromagnetic smog that interferes with sensitive astronomical observations. Radio telescopes on Earth, no matter how remote their location, are constantly battling this terrestrial interference, limiting their ability to detect faint signals from the distant cosmos. The Moon's far side, however, offers a unique sanctuary. Shielded by the immense bulk of the moon itself, it is naturally protected from the vast majority of Earth-generated radio noise. It's like finding the quietest room in a bustling metropolis, a place where the faint whispers of the universe can finally be heard without interruption. Imagine a powerful radio telescope array nestled in a far-side crater, its sensitive dishes pointed towards the pristine depths of space. Such an observatory could revolutionize our understanding of the early universe, detecting faint signals from the epoch of reionization, when the first stars and galaxies ignited and flooded the cosmos with light. These early signals, stretched by the expansion of the universe, manifest as very low-frequency radio waves, precisely the kind that are most susceptible to Earth-based interference. A far-side radio observatory could also conduct unprecedented searches for extraterrestrial intelligence, SETI, listening for artificial signals from other civilizations without the masking effect of human-generated noise. This quiet zone isn't just a desirable location, it's an essential one for pushing the boundaries of radio astronomy and fundamental cosmology. It presents an opportunity to see and hear the universe in a way that is simply impossible from Earth. What profound insights into the origins of everything, what startling revelations about life beyond Earth await us in this cosmic silence. The hidden hemisphere promises an acoustic window into the universe's grandest secrets.
The moon's surface, particularly its hidden hemisphere, is a testament to billions of years of relentless geological processes, primarily driven by impact events. Unlike Earth, which is constantly reshaped by plate tectonics, volcanism, and erosion from wind and water, the moon is a largely static body. Its geology is a frozen record of its ancient past. The overwhelming feature on the far side is the sheer density of impact craters. These circular depressions, ranging from microscopic pits to vast basins spanning hundreds of kilometers, are the scars left by countless asteroids, comets, and meteoroids slamming into the lunar surface. The lack of an atmosphere means no protection from these incoming projectiles, and the absence of significant geological activity or erosion means these scars persist for billions of years, creating a geological timeline etched in stone. The formation of the moon's regolith is another critical geological process. This powdery, fractured layer, sometimes several meters thick, is not soil in the terrestrial sense, as it lacks organic material. Instead, it's a consequence of continuous bombardment. Each impact, from micrometeorites to large asteroids, shatters and pulverizes the underlying rock, creating a blanket of fine dust and rock fragments. This regolith poses both a challenge and an opportunity for future lunar missions. It's abrasive and can damage equipment, but it also contains valuable resources, including the aforementioned helium-3 and potentially water ice. While large-scale volcanism, which formed the near-side Maria, is conspicuously absent on the far side, there is evidence of localized volcanic activity, particularly within some of the larger basins. These basaltic flows are far less extensive, however, reinforcing the notion of a thicker, more resistant crust on this hidden face. The diverse terrains of the far side, from the ancient, heavily cratered highlands to the massive SPA basin, are a direct result of these long-term geological forces, offering a pristine, undisturbed record of the early solar system's violent history. What stories are etched into this ancient lunar canvas, waiting for us to decipher their meaning? The answers lie in the very dust beneath our feet, or rather, our rover's wheels.
The profound geological differences between the moon's near and far sides have spurred a fascinating scientific debate, leading to several compelling theories about its asymmetric formation. The dominant theory for the moon's overall genesis is the giant impact hypothesis, which posits that a Mars-sized protoplanet, often called Theia, collided with early Earth, ejecting a vast cloud of superheated debris that eventually coalesced to form our moon. While this explains the moon's existence and its composition, it doesn't fully account for the dramatic near-side-far-side dichotomy.
One leading explanation for this asymmetry, as mentioned earlier, is the thermal evolution model. In this scenario, the newly formed moon, initially much closer to a still molten Earth, experienced differential heating. The near side, constantly exposed to the intense thermal radiation from Earth, would have remained hotter and therefore had a thinner, more easily punctured crust. The far side, shielded from this intense heat, would have cooled more rapidly, developing a thicker, more rigid crust that resisted large-scale volcanic eruptions. This preferential thinning of the near-side crust allowed molten basaltic lava to flow more easily onto the surface, forming the expansive maria we see today, while the far side remained largely free of such inundations. Another intriguing, though more speculative hypothesis involves a second moon. This theory suggests that after the giant impact, two moons formed from the debris cloud, a larger moon and a smaller companion. Over millions of years, gravitational interactions led to the smaller moon slowly drifting towards the larger one, until, in a slow-motion collision, it gently accreted onto the larger moon's far side. This splat, or pancake impact, as it's sometimes described, would have added a significant layer of material to the far side, explaining its thicker crust and lack of maria. While evidence for this second moon theory is still being gathered and debated, both it and the thermal evolution model offer plausible explanations for the dramatic differences we observe. The ongoing exploration of the hidden hemisphere, particularly within the South Pole Aitken Basin, is providing crucial data to test these hypotheses, allowing scientists to piece together the complex, chaotic history of our celestial companion. What profound insights into planetary formation? What unexpected twists in our moon's dramatic birth story will future missions reveal? The secrets are locked in the very rocks and craters of this enigmatic lunar face.
The journey to understand and explore the moon's hidden hemisphere is intertwined with some of the most dramatic chapters in space exploration history. While Luna 3 provided the first tantalizing glimpse in 1959, it was the subsequent American Apollo program that truly brought humans to the moon, albeit always to its near side. Yet even during the Apollo era, the far side played a crucial, if indirect, role. The Apollo 8 mission in December 1968, famously the first human mission to orbit the moon, provided humanity with its first direct visual observations of the far side from a human perspective. Astronauts Frank Borman, James Lovell, and William Anders described a starkly different, heavily cratered landscape compared to the familiar Maria-dominated near side. Anders' iconic Earthrise photograph, taken while orbiting the moon, vividly illustrated the desolate, alien beauty of the lunar landscape, a landscape which included vast stretches of the previously unseen far side. This human perspective ignited public imagination and deepened the scientific curiosity about this hidden realm. The Apollo missions, despite not landing on the far side, gathered vital data from orbit that contributed to our understanding of its geological composition and gravity field. Subsequent robotic missions from various nations continued to chip away at the far side's mysteries. Lunar orbiters from the US, Europe, Japan, and India have meticulously mapped its topography, identified potential water ice deposits, and analyzed its mineralogical composition. Each mission, whether a flyby, an orbiter, or a soft lander, has added another piece to the complex puzzle of the hidden hemisphere. China's Chang'e program, particularly Chang'e 4, represents the culmination of decades of incremental progress, daring to attempt a soft landing in a region deemed too challenging by previous generations of space agencies. These historical milestones, from the first grainy images to the first robotic landing, are not just technical achievements. They are testaments to humanity's insatiable drive to explore, to push beyond the known, and to confront the unknown, no matter how daunting.
What new historical milestones, what daring feats of exploration will mark the next chapter in humanity's quest to understand the moon's deeper mysteries? The narrative of exploration is far from over. While the allure of the moon's hidden hemisphere is undeniable, it's crucial to acknowledge the significant challenges and scientific counterarguments that temper some of the more optimistic visions. The extraction of resources like helium-3, for example, is not a trivial undertaking. As discussed, helium-3 is not found in concentrated deposits, but is diffused throughout the lunar regolith. Extracting it would require processing enormous quantities of lunar soil, heating it to hundreds of degrees Celsius, and then separating the trace amounts of helium-3. This would demand massive energy inputs and sophisticated heavy machinery, all of which would need to be launched from Earth at considerable cost. Critics argue that the energy return on investment, EROI, for lunar helium-3 mining might not be favorable, especially in the near term. A 2019 study in Nature Geoscience, for instance, highlighted the significant engineering hurdles and the sheer scale of operations required, suggesting that the economic feasibility remains highly speculative without significant breakthroughs in fusion technology itself. Similarly, while water ice is present, its exact concentration and accessibility are still being assessed. Some estimates suggest that the water might be mixed with lunar dust and rocks, making extraction and purification more complex than simply scooping up frozen chunks. The extreme cold and perpetual darkness of the permanently shadowed regions also pose formidable engineering challenges for any machinery operating there, requiring specialized power systems and thermal management. Furthermore, the idea of a radio-quiet zone on the far side, while scientifically sound, isn't entirely without its own complexities. Establishing and maintaining a large-scale observatory would still require a considerable infrastructure, including power generation, human habitation modules, if crewed, and communication systems to Earth, all of which could generate some degree of local interference. There are also ongoing debates about the precise mechanisms behind the moon's asymmetric formation, with various models presenting different strengths and weaknesses, none definitively accepted as the sole explanation. These counterarguments and challenges are not meant to dampen enthusiasm, but rather to ground our aspirations in scientific reality, emphasizing the immense engineering and scientific ingenuity required to truly unlock the hidden hemisphere's full potential. What are the true costs? What are the real limits to humanity's ambitious reach for the lunar frontier? The road ahead is paved with both promise and formidable obstacles.
The exploration of the moon's hidden hemisphere holds profound implications for the establishment of future lunar bases, transforming our vision from temporary flag-planting exercises to long-term sustainable outposts. The initial wave of lunar exploration, particularly the Apollo program, was characterized by short stays and limited objectives. However, the discovery of water ice, particularly at the lunar poles, including those on the far side within the South Pole Aitken Basin, fundamentally alters this paradigm. Water is not just for drinking, it's the raw material for breathable air and, most importantly, rocket propellant. This concept, known as in situ resource utilization, or ISRU, is a cornerstone of future lunar colonization. Imagine a lunar base that can live off the land, producing its own water, oxygen, and fuel from local resources. This drastically reduces the logistical burden and cost of resupply missions from Earth, making long-duration stays and even permanent settlements a tangible reality rather than a distant dream. A base on the moon's far side, while presenting unique communication challenges, also offers distinct advantages. As discussed, its unparalleled radio-quiet environment makes it an ideal location for astronomical observatories, providing a compelling scientific justification for a permanent human presence. Furthermore, the far side's thicker crust and ancient, heavily cratered terrain represent a pristine geological record, offering scientific opportunities unavailable on the near side. Future lunar bases might not be single monolithic structures, but a distributed network of facilities, each optimized for specific functions. A polar base focused on water ice extraction, a far-side observatory dedicated to radio astronomy, and perhaps even experimental mining operations for helium-3. The design of these bases would need to be radically different from anything seen on Earth, engineered to withstand extreme temperatures, pervasive dust, and constant radiation. Robotic construction, utilizing lunar regolith as building material, could play a pivotal role, reducing the need for massive launches from Earth. Our quest to conquer the hidden hemisphere is no longer just about curiosity. It's about establishing humanity's first permanent foothold beyond our home planet, a dramatic step in our evolution as a spacefaring species. What will life be like in these lunar outposts? A testament to our ingenuity and daring. The blueprint for humanity's cosmic future is being drawn on the moon's hidden face.
The discovery of water ice on the moon, particularly in its permanently shadowed regions, prompts fascinating astrobiological parallels with the search for life beyond Earth. While the moon itself is not considered a habitable body in the conventional sense, it lacks an atmosphere, liquid water on its surface, and a protective magnetic field, the presence of water ice significantly broadens our understanding of where water can persist in the solar system. This has direct implications for our understanding of habitability on other celestial bodies. For instance, the mechanisms by which water ice is preserved in lunar PSRs provide valuable insights for exploring other cold, airless bodies like the poles of Mercury or icy moons in the outer solar system, such as Europa and Enceladus, where subsurface oceans are believed to exist. The moon serves as a nearby, accessible laboratory for studying the processes that could lead to the formation and preservation of water on a planetary body. Moreover, the search for life often begins with the search for water. While lunar water ice is unlikely to harbor indigenous life, its presence raises philosophical questions about the universality of water as a prerequisite for life and how widely it might be distributed across the cosmos. Could ancient cometary impacts, which delivered water to the moon, have also seeded other, more habitable worlds with the essential building blocks of life? The study of lunar water, its origin, and its long-term stability helps refine our models for planetary accretion and the delivery of volatiles, the light elements crucial for biological processes, to nascent planets. It underscores the interconnectedness of seemingly disparate scientific fields. The moon's hidden hemisphere, once viewed as barren and irrelevant to astrobiology, now offers crucial data points in humanity's grandest quest, the search for extraterrestrial life. What fundamental insights into the cosmic recipe for life will these icy lunar secrets eventually unlock? The moon, in its silent wisdom, might hold clues to life's grand tapestry beyond Earth.
A comprehensive understanding of the moon's hidden hemisphere necessitates a comparative analysis with its familiar near side, highlighting the stark contrasts that define our natural satellite. The most striking difference, as we've explored, is the distribution of Maria. The near side is dominated by vast, dark basaltic plains, which cover approximately 30% of its surface. These Maria formed from ancient volcanic eruptions that filled immense impact basins with molten lava. In contrast, the far side has very few Maria, covering less than 1% of its surface, leaving it largely composed of bright, heavily cratered highlands. This difference is directly linked to the significantly thicker crust on the far side, which inhibited the widespread eruption of molten rock. The far side's highlands are also generally older and more heavily cratered than the near side, providing a more pristine record of the early solar system's intense bombardment period. The craters on the far side tend to be better preserved, lacking the erosion or burial by later volcanic flows seen on the near side. Beyond topography, there are subtle but significant differences in mineralogy and gravitational anomalies. The near side exhibits stronger gravitational variations,
partly due to the presence of large mass concentrations, mass cons, beneath the Maria. The far side, with its more uniform crustal thickness, generally shows weaker gravitational anomalies. The distribution of elements like thorium and potassium, indicators of past volcanic activity, also varies, with higher concentrations observed on the near side. Furthermore, the Moon's core and mantle structure may also be slightly asymmetric, with theories suggesting a slightly offset core or differences in mantle convection patterns that contributed to the crustal dichotomy. This comparative analysis is not merely an academic exercise. It provides crucial data for understanding the fundamental processes that shaped planetary bodies. By studying the profound differences on a single celestial object, we gain insights into the complex interplay of internal heat, external impacts, and gravitational forces that dictate a planet's evolution. What profound lessons about planetary evolution, what fundamental truths about our cosmic neighborhood can we glean from this celestial tale of two halves? The Moon itself is a living textbook of planetary science.
For millennia, the Moon's hidden hemisphere, or dark side as it was popularly, though inaccurately, known, has been a source of profound fascination, inspiring myths, legends, and philosophical reflections. Before Luna 3's reveal, the far side was a blank slate, a repository for humanity's deepest curiosities and wildest imaginings. It was the ultimate unknown, a symbol of what lay beyond human perception. This historical perception of a dark side isn't just about lack of light. It evokes a sense of mystery, of something hidden, perhaps even sinister or foreboding. It fueled theories of hidden alien bases, secret civilizations, or strange, unearthly phenomena shielded from our view. This cultural narrative played a significant role in popular culture, from science fiction novels to conspiracy theories, shaping the collective human psyche's relationship with its closest cosmic neighbor. The very phrase, "dark side of the Moon," entered common parlance, synonymous with anything hidden, enigmatic, or mysterious. Even after the scientific revelation that the far side receives just as much sunlight as the near side over the course of a lunar month, the mystique has persisted. The actual scientific term, far side, has struggled to fully displace the more evocative dark side in popular imagination, a testament to the power of ingrained cultural narratives. The exploration of this hidden face, therefore, is not just a scientific endeavor, it's a symbolic one, a journey into the last great terrestrial unknown. It represents humanity's push against the boundaries of perception, our innate desire to unveil what is concealed. From the ancient astronomers who painstakingly charted the visible face, to the robotic explorers mapping its hidden counterpart, the story of the Moon's far side is deeply entwined with the history of human curiosity. What ancient fears, what primordial sense of wonder does the dark side still evoke in the human spirit, even in an age of scientific enlightenment? The enigma of the hidden hemisphere continues to resonate deeply within us, a mirror reflecting our own profound curiosity about the universe.
Beyond its visible features, the Moon's hidden hemisphere holds even more subtle and profound scientific mysteries. One such enigma is the presence of magnetic anomalies on the far side, remnants of a long-dead lunar magnetic field. Unlike Earth, which possesses a strong, active global magnetic field generated by its molten iron core, the Moon's internal dynamo appears to have ceased billions of years ago. However, scattered regions of magnetism persist in the lunar crust, particularly on the far side. These fossilized magnetic fields, known as lunar swirls when associated with bright albedo features, are a puzzle. Some theories suggest they are remnants of a stronger ancient lunar dynamo, preserved in certain crustal rocks.
Others propose that these localized magnetic fields were induced by ancient impact events, where the energy of the impact created transient magnetic fields that imprinted themselves on the surrounding rock. Understanding these magnetic anomalies provides crucial insights into the Moon's internal structure and its thermal and magnetic evolution over geological time. They are like faint echoes of a powerful, ancient force that once protected the Moon, much like Earth's magnetic field shields us today. Another captivating avenue of research involves lunar seismology, the study of moonquakes. Apollo missions deployed seismometers on the near side that detected thousands of moonquakes, mostly very weak, caused by tidal stresses from Earth or meteorite impacts. While no seismometers have yet been deployed on the far side, future missions could provide invaluable data. By placing seismometers on both the near and far sides, scientists could precisely triangulate the origins of moonquakes and gain an unprecedented understanding of the Moon's deep interior, including the size and state of its core. Could there be significant differences in seismic activity or wave propagation on the far side due to its thicker crust or different underlying mantle composition? These seismic whispers from the Moon's depths could reveal the ultimate secrets of its formation and evolution, much like how seismic waves are used to map Earth's interior. What hidden processes, what internal dynamics are still at play beneath the silent, cratered surface of the Moon's enigmatic far side? The quest for answers leads us deeper, both into the lunar crust and into the very heart of planetary science.
The future of lunar exploration, particularly focusing on the hidden hemisphere, is bright, with several ambitious missions on the horizon. NASA's Artemis program stands at the forefront of this new era, aiming to return humans to the Moon, including the first woman and person of color, and to establish a sustainable presence there. While early Artemis missions will likely focus on the lunar South Pole, which technically straddles both near and far sides due to illumination conditions, but whose permanently shadowed regions are often considered far side-like in their challenges and potential resources, the long-term vision certainly encompasses the far side. The development of advanced communication relays, like the proposed Lunar Gateway, a small space station orbiting the Moon, will be crucial for facilitating sustained human and robotic operations on the far side. The gateway will act as a staging post and communication hub, circumventing the direct line of sight challenge. Beyond Artemis, other nations and private companies are also setting their sights on the hidden hemisphere. Russia has expressed interest in its own lunar missions, potentially targeting the far side. Commercial lunar landers developed by private companies under NASA's Commercial Lunar Payload Services, or CPLS, initiative could also open up new opportunities for scientific investigations on the far side, providing more frequent and cost-effective access. These future missions will aim to refine our understanding of water-ice distribution and accessibility, conduct more detailed geological surveys, and potentially even deploy the first dedicated far-side radio observatories. The engineering challenges are immense, from developing robust lunar surface systems capable of operating in extreme environments to ensuring reliable power generation and communication links. Yet the scientific and strategic rewards are equally immense. The coming decades promise an unprecedented surge in lunar exploration, transforming the Moon, and especially its hidden hemisphere, from a distant enigma into a vibrant hub of human activity and scientific discovery. What grand endeavors, what groundbreaking discoveries will define this next chapter of humanity's lunar quest? The hidden hemisphere beckons, a silent promise of future glory.
While the potential of lunar resources, particularly water ice and helium-3, is a major driver for far-side exploration, the transition from theoretical possibility to practical resource extraction is fraught with formidable challenges.
The initial enthusiasm for lunar mining must be tempered by engineering realities and economic considerations. For water ice, the process involves locating sufficient quantities, excavating the regolith, which is abrasive and can clog machinery, heating it to sublimate the ice into water vapor, and then condensing and purifying the water. This requires significant power, which must be generated on the lunar surface, potentially through solar arrays or small fission reactors. The extreme cold of the permanently shadowed regions also complicates matters, as equipment must be designed to operate reliably at temperatures far below anything experienced on Earth. Furthermore, the precise chemical form of lunar water, whether it's pure ice, hydrated minerals, or adsorbed water on dust grains, influences the extraction method and efficiency. The challenges for helium-3 mining are even greater. The low concentration of helium-3 in the regolith means processing vast quantities of material to yield even small amounts of the isotope. As discussed, this involves heating the regolith to very high temperatures, which is incredibly energy-intensive. Transporting the mined helium-3 back to Earth would also be a colossal logistical and economic undertaking, requiring highly efficient and reliable space transportation systems. Moreover, the economic viability of helium-3 hinges entirely on the successful development and widespread commercialization of fusion power on Earth, which is still decades away. Beyond the technical hurdles, there are also legal and ethical considerations surrounding lunar resource extraction. Who owns the resources on the Moon? What are the international regulations governing their extraction and commercialization? These questions, addressed in treaties like the Outer Space Treaty, are complex and require international cooperation to resolve. While the promise of lunar resources is real, the journey from speculation to large-scale reality is a long one, requiring sustained investment, technological innovation, and careful international deliberation. What are the true costs? What are the real breakthroughs needed to turn lunar dreams into tangible assets? The challenges are as vast as the lunar landscape itself.
The exploration of the Moon's hidden hemisphere transcends mere scientific and technological achievements. It carries profound philosophical implications for humanity's place in the cosmos and its future trajectory. For millennia, the Moon has been a constant, visible companion, a symbol of constancy and comfort. Yet, the realization of a perpetually hidden side, a vast, unknown frontier just beyond our direct perception, adds a new layer of complexity to our relationship with it. It challenges our anthropocentric view of the universe, reminding us that even our closest celestial neighbor holds secrets we are only just beginning to unravel. The journey to the far side is a powerful metaphor for humanity's innate drive to explore, to push beyond the boundaries of the known, to confront the unknown not with fear, but with curiosity and determination. It speaks to our species' unique capacity for wonder and discovery. As we consider establishing permanent outposts on this hidden face, extracting its resources, and using it as a stepping stone to the stars, we are confronted with questions about our cosmic destiny. Are we destined to remain confined to Earth, or is our future truly multiplanetary? The Moon's far side, with its potential for self-sufficiency and its unique scientific advantages, offers a compelling argument for the latter. It represents a crucible for developing the technologies and social structures necessary for long-duration space habitation, preparing us for even grander voyages to Mars and beyond. The challenges of living and working on the far side, the isolation, the reliance on technology, and the necessity of international cooperation will force us to confront fundamental questions about human nature, adaptability, and resilience. This is not just about scientific progress, it's about defining what it means to be human in an expanding universe. What profound transformations, What new understandings of ourselves will arise from this daring step onto the hidden side of our silent companion? The hidden hemisphere is not just a destination, it is a mirror reflecting our own cosmic aspirations.
The potential for the moon's far side as an unprecedented radio quiet zone extends beyond merely detecting faint signals from the early universe or searching for alien intelligence. It broadens the horizons of radio astronomy in ways that are simply impossible from Earth. Imagine telescopes capable of detecting minute changes in the cosmic microwave background, the afterglow of the Big Bang, providing insights into the universe's earliest moments with unparalleled precision. The lack of atmospheric distortion and ionospheric interference on the far side would also allow for observations at very low frequencies, which are almost entirely blocked by Earth's ionosphere. These low-frequency observations could open up entirely new windows into astrophysical phenomena, from distant exoplanets to solar radio bursts, providing data that fundamentally reshapes our understanding of the universe. Furthermore, the far side offers a unique environment for testing new astronomical instrumentation and techniques. With minimal interference, engineers could deploy highly sensitive, experimental arrays without the constant struggle against terrestrial noise. This could accelerate the development of next-generation radio telescopes, pushing the boundaries of what's detectable. Beyond pure science, the establishment of far-side observatories could foster international collaboration on a scale rarely seen, uniting nations in a shared quest for knowledge. The moon's hidden hemisphere could become a truly global scientific outpost, a testament to humanity's collective pursuit of cosmic understanding. The journey to the far side is not just about exploring a new lunar landscape. It's about opening up entirely new realms of scientific inquiry, allowing us to perceive the universe with unparalleled clarity and depth. What unimaginable discoveries, what paradigm shifts in our cosmic understanding await us in the profound silence of the moon's hidden face? The universe is waiting to whisper its deepest secrets.
The geological story of the moon's far side is a continuing drama, rooted in the very beginnings of our satellite's existence. Following the giant impact that formed the moon, it is believed to have been largely molten, a swirling magma ocean. As this ocean gradually cooled and solidified, lighter minerals, primarily anorthosite, floated to the surface, forming the moon's primordial crust. This global crust was not uniformly thick, and the subsequent evolution of this initial asymmetry is key to understanding the far side. One of the prevailing theories for the crustal dichotomy, as mentioned, points to the lingering thermal influence of the early Earth. The side of the moon facing Earth was subjected to intense radiation from our still molten planet, keeping its near-side crust warmer and thinner for a longer period. This allowed internal molten material, primarily basaltic lava, to more easily rise to the surface through fissures and impact basins, forming the vast Maria. The far side, however, shielded from Earth's intense heat, cooled more rapidly and developed a significantly thicker crust. This thicker, more rigid crust acted as a formidable barrier, largely preventing large-scale volcanic eruptions. Even when massive impacts occurred on the far side, such as the one that created the colossal South Pole Aitken Basin, the sheer thickness of the crust meant that molten material from the mantle was less likely to well up and fill the basin, explaining its dry appearance compared to the near-side Maria. Furthermore, differences in the moon's interior structure, potentially an uneven distribution of heat-producing elements in the mantle or a slightly offset core, could have also contributed to this asymmetry. The internal dynamics, coupled with external gravitational forces and impact events, sculpted a moon of two dramatically different halves. Each new piece of data from missions like Chang'e 4 and from orbital observations refines our models and adds new layers to this ancient geological drama. What subtle clues, what forgotten chapters of the moon's early life are still hidden within the rocks and craters of its enigmatic far side, waiting to complete this epic tale? The moon's surface is a silent archive of its turbulent genesis.
Let's venture into the realm of hypothetical scenarios.
allowing our imaginations to explore what life might be like on a far-side lunar base in the distant future. Picture a multi-domed habitat nestled within the rim of a crater, perhaps within the South Pole Aitken Basin itself. The domes, likely constructed from lunar regolith using advanced 3D printing techniques, would be shielded against solar radiation and micrometeorite impacts by layers of lunar soil. Inside, a carefully controlled environment, recycled air, hydroponic gardens providing fresh food, and water meticulously extracted from nearby ice deposits. Power would likely come from small nuclear fission reactors, providing a reliable energy source even during the long 2-week lunar night. Communication with Earth would be an indirect ballet, relayed through the Queqiao-like satellites strategically positioned at the Earth-Moon L2 Lagrange point, creating a slight time delay but a vital link to home. Daily life for lunar pioneers would be a blend of scientific exploration and resource management. Astronauts and researchers, clad in advanced spacesuits, would conduct geological surveys, operate robotic mining equipment, and maintain the delicate machinery of the Farside Radio Observatory. The silence would be profound, broken only by the hum of life support systems and the distant chatter from Earth relayed through the communication network. This isolation, while challenging, would also offer unparalleled scientific opportunities, particularly for deep space astronomy. The very remoteness of the far side, its isolation from Earth's interference, would be its greatest asset. Recreational activities might include virtual reality experiences simulating terrestrial landscapes, or perhaps even lunar sports adapted to the low gravity. The psychological impact of living on a world where Earth is never visible would be a unique challenge, fostering a deep connection to the cosmos and a new perspective on our home planet. This is more than just science fiction. It is a vision that humanity is actively striving to achieve, pushing the boundaries of our presence beyond Earth. What new human experiences, what unprecedented challenges and triumphs await those brave enough to call the hidden hemisphere home? The future is a canvas waiting to be painted, one lunar module at a time.
NASA's Artemis program, while initially focused on the lunar South Pole due to its water ice potential, has long-term goals that undeniably point towards the Moon's hidden hemisphere. The phased approach of Artemis, starting with uncrewed tests like Artemis 1, followed by crewed orbital missions like Artemis 2, and culminating in human landings with Artemis 3 and beyond, is building the foundational capabilities for a sustained lunar presence. The development of the Lunar Gateway, a critical component of Artemis, will be instrumental for far-side operations. Positioned in a unique halo orbit around the Moon, the Gateway will offer unprecedented access to various lunar regions, including the far side. It will serve as a science laboratory, a temporary habitat for astronauts, and most crucially, a communication relay station, bypassing the line-of-sight issue that currently plagues far-side missions. This modular station will be a proving ground for technologies and procedures essential for deeper space exploration. Beyond the immediate goal of returning humans, Artemis aims to establish a long-term human presence on the Moon, a concept referred to as sustainable lunar exploration. This involves building lunar habitats, developing in-situ resource utilization, or ISRU capabilities, and conducting cutting-edge scientific research. The far side, with its pristine radio environment and unique geological history, offers compelling scientific rationales for significant Artemis investment. Future Artemis missions could include robotic landers and rovers specifically designed for far-side exploration, potentially followed by human expeditions. The goal is not just to visit, but to live and work on the Moon, utilizing its resources to enable missions to Mars and beyond.
The Artemis program represents a paradigm shift from the flags and footprints approach of Apollo to a more ambitious vision of permanent human settlement. The hidden hemisphere, once a remote enigma, is now firmly within the sights of humanity's grandest space exploration endeavor. What engineering marvels, what scientific breakthroughs will Artemis achieve on the moon's secluded face, shaping the trajectory of human civilization among the stars? The cosmic frontier is expanding, and the moon's far side is the next great step.
While the narrative of lunar exploration, particularly concerning the hidden hemisphere, often emphasizes its adventurous and dramatic potential, it's vital to address mainstream scientific counterarguments and skepticism surrounding certain claims. For instance, the economic feasibility of large-scale helium-3 mining remains a contentious issue. While the resource is undeniably present, the sheer scale of the operation required to extract it in commercially viable quantities, coupled with the high energy demands and the uncertainty of future fusion power development, leads many economists and some planetary scientists to view it as a distant, perhaps even unachievable prospect in the near to medium term. Critics argue that the significant investment required for such an endeavor might be better allocated to developing terrestrial clean energy sources or focusing on more readily accessible lunar resources like water ice. A 2023 review published in Science echoed these sentiments, highlighting the significant technical and economic hurdles that still need to be overcome before helium-3 can be considered a practical energy solution. Similarly, while the far side offers an ideal radio quiet zone, the challenges of establishing and maintaining a sophisticated observatory there are substantial. The extreme thermal cycling, the abrasive regolith, and the communication latency all present formidable engineering obstacles. The reliance on relay satellites introduces points of failure and adds complexity to operations. Some researchers argue that while a far-side observatory is scientifically desirable, smaller, more localized radio quiet zones on Earth, coupled with advanced signal processing techniques, might offer a more cost-effective approach for certain types of observations in the interim. This skepticism is not meant to negate the potential of the far side, but to provide a balanced perspective, acknowledging the significant scientific and engineering challenges that must be overcome. It emphasizes that ambitious visions, while inspiring, must be grounded in rigorous scientific assessment and technological realism. What are the true limits of our ambition, and how do we balance the audacious dreams of exploration with the practical realities of engineering and economics? The journey to the hidden hemisphere is a testament to both human ingenuity and the humbling vastness of the challenges ahead.
The exploration of the moon's hidden hemisphere is not an end in itself. It is a critical stepping stone in humanity's broader vision of space colonization. Every successful mission to the far side, every scientific discovery, and every technological breakthrough contributes to a cumulative knowledge base that is directly applicable to establishing permanent human settlements beyond Earth. The challenges encountered on the far side, developing robust life support systems, managing radiation exposure, perfecting in situ resource utilization, or ISRU, and mastering long-duration communication are precisely the challenges that must be overcome for any sustained human presence on Mars or other celestial bodies. The Moon, and particularly its far side due to its unique characteristics and resource potential, serves as an invaluable proving ground. It allows us to test new technologies, refine operational procedures, and understand the physiological and psychological impacts of long-term space habitation in a relatively accessible environment. Consider the development of closed-loop life support systems. On Earth, we take air, water, and food for granted. In space, these must be meticulously recycled and produced. The experience gained in building and operating such systems on a lunar far-side base will be directly transferable to a Martian habitat. Similarly, techniques for extracting and processing water ice on the Moon will inform future efforts to utilize Martian polar ice or water locked in asteroids. The human experience of living in isolation, far from Earth's familiar comforts, will also provide invaluable psychological data for planning future deep space missions.
The Moon, therefore, becomes humanity's first extraterrestrial university, with the far side serving as its most advanced and challenging campus. The lessons learned here will be foundational for our journey to become a true multi-planetary species. What grander frontiers, what deeper cosmic destinies will be unlocked by the knowledge gained from our pioneering efforts on the hidden hemisphere? The exploration of the Moon is a prelude to humanity's future among the stars.
The prevalence of anorthosite on the Moon's far side, particularly in its heavily cratered highlands, is not just a curious geological feature. It's a profound window into the Moon's very origins. Anorthosite is a light-colored, igneous rock, rich in the mineral plagioclase feldspar. On Earth, anorthosite is relatively rare, found in ancient continental shields. On the Moon, it forms the bulk of the lunar highlands, and its abundance on the far side is striking. The prevailing theory for its formation is linked to the magma ocean hypothesis. Immediately following the giant impact event that formed the Moon, our nascent satellite was likely a vast ocean of molten rock. As this magma ocean gradually cooled, heavier minerals sank to the bottom, while lighter, less dense minerals, like plagioclase feldspar, crystallized and floated to the surface, forming the Moon's primordial crust. This crust was predominantly anorthositic. The reason for its greater exposure and thickness on the far side is tied to the differential cooling and subsequent geological evolution. While the near side experienced extensive volcanic activity, driven by a thinner crust and potentially localized heat sources, the far side's thicker anorthositic crust remained largely intact, acting as a resilient shield against widespread basaltic flooding. The ancient highlands of the far side are essentially preserved remnants of the Moon's earliest crust, offering scientists a direct sample of the processes that occurred during the final stages of lunar accretion and differentiation. By studying the composition and structure of these anorthositic terrains, missions like Chang'e 4 and future endeavors can piece together the precise timeline of the Moon's solidification, the evolution of its internal heat, and the earliest conditions on a planetary body. It's like discovering an untouched ancient manuscript, perfectly preserved, offering original insights into a forgotten era. What secrets of planetary formation, what pristine clues about the birth of worlds are forever etched within these bright, ancient rocks of the hidden hemisphere? The anorthosite of the far side is a tangible link to the Moon's violent and fiery youth.
The Moon's far side is not only a destination, but also a crucial component of humanity's larger strategy for deep space exploration. Future missions targeting this hidden hemisphere will leverage and contribute to the infrastructure required for voyages beyond the Earth-Moon system. The Lunar Gateway, a more reliable internet in space. Furthermore, the scientific infrastructure developed on the far side, particularly the radio-quiet observatories, will serve a dual purpose, advancing fundamental astronomy while also providing vital data for future long-duration missions. For example, deep space navigation requires extremely precise measurements of celestial objects, which far-side observatories could provide. The hidden hemisphere, therefore, is not merely a scientific curiosity or a resource goldmine. It is an indispensable training ground and a critical logistical node in humanity's journey to becoming a truly interplanetary species. What further reaches of the cosmos, what new frontiers of human exploration will be made possible by our mastery of the Moon's enigmatic far side? The future of deep space exploration begins on our closest neighbor.
To truly grasp the enigma of the Moon's hidden hemisphere, we must revisit the fundamental principle of tidal locking, a cosmic ballet that has profoundly shaped our Moon's appearance. It's not simply that the Moon doesn't rotate, it rotates once per orbit. This delicate balance is achieved through a long, drawn-out process of gravitational interaction between Earth and its Moon. Early in their history, the Moon likely rotated much faster than it does today. However, Earth's immense gravitational pull
created tidal bulges on the moon, much like the moon creates tides in Earth's oceans. These bulges were not perfectly aligned with the Earth-Moon axis because of the moon's rotation. The gravitational pull of Earth on these misaligned bulges created a torque, a twisting force, that gradually slowed the moon's rotation over billions of years. This process continued until the moon's rotation period matched its orbital period, at which point the tidal bulges became perfectly aligned with Earth, and the torque ceased. This means that one hemisphere is always facing Earth, while the other is perpetually turned away. It's not a dark side in terms of light, as both sides experience approximately 2 weeks of sunlight followed by 2 weeks of darkness during a lunar month. Instead, it's a hidden side from an earthbound perspective. This tidal locking has had profound consequences for the moon's geological evolution. The constant gravitational tug from Earth exerted stress on the moon's interior, potentially influencing the distribution of its molten material and contributing to the crustal asymmetry we observe. The differential heating from the early Earth, as discussed, would have been exacerbated by this tidal interaction, leading to a thinner crust on the near side. Understanding tidal locking is fundamental to comprehending why the moon presents two such distinct faces, one familiar and one enigmatic. It's a subtle but powerful force, shaping celestial bodies across the cosmos. What other planetary puzzles, what further revelations about the dance of cosmic bodies can we decipher by studying the intricate dynamics of tidal locking across the solar system? The moon is a prime example of its profound influence.
The moon, in its silent grandeur, has always held a special place in the human psyche. From ancient myths that saw it as a deity or a celestial clock, to the modern scientific endeavors that seek to unlock its deepest secrets, our connection to the moon is profound and enduring. The exploration of its hidden hemisphere amplifies this connection, adding layers of mystery, adventure, and drama to an already rich narrative. It reminds us that even the most familiar objects in our cosmic neighborhood can hold astonishing surprises, challenging our preconceived notions and igniting our innate curiosity. The journey to the far side is a testament to humanity's unyielding drive to explore, to push the boundaries of knowledge, and to venture into the unknown. It reflects our species' unique ability to dream, to innovate, and to persevere in the face of immense challenges. Every image transmitted from the far side, every scientific discovery, and every step taken by a rover or, hypothetically, a human on its ancient surface is a step forward for all of humanity. It expands our cosmic horizons, broadens our understanding of planetary evolution, and offers tantalizing glimpses of a future where humanity is a multi-planetary species. The moon is not merely a lifeless rock. It is a celestial mirror, reflecting our aspirations, our ingenuity, and our enduring quest for knowledge. The moon's far side, once a symbol of the unattainable, is transforming into a frontier of unprecedented opportunity, a place where our future in space will truly take shape. It is a canvas upon which humanity continues to paint its cosmic destiny. One scientific breakthrough, one technological marvel, one philosophical revelation at a time. What new stories, what deeper connections will our ongoing exploration of the hidden hemisphere forge between humanity and its silent celestial companion? The journey to the moon's far side is, in essence, a journey into ourselves.
The story of the moon's hidden hemisphere is far from over. It is an unending story of scientific discovery, technological innovation, and human ambition. Each mission,
Each new piece of data adds another chapter to this captivating narrative. The scientific community continues to analyze the vast data sets gathered by lunar orbiters and landers, constantly refining our understanding of the far side's geological history, its internal structure, and its resource potential. New theories about its formation are being proposed and tested, pushing the boundaries of planetary science. Engineers are tirelessly working on developing the next generation of lunar landers, rovers, and habitats designed to operate in the challenging far-side environment. They are conceptualizing innovative solutions for communication, power generation, and resource extraction, turning what was once science fiction into engineering reality. Perhaps most importantly, the ongoing exploration of the far side continues to inspire a new generation of scientists, engineers, and explorers. The allure of the unknown, the promise of groundbreaking discoveries, and the vision of humanity's expansion into the cosmos are powerful motivators. As we move forward, the Moon's hidden hemisphere will become increasingly accessible, transforming from a remote enigma into a bustling hub of human and robotic activity. It will serve as a crucial testbed for technologies needed for missions to Mars and beyond, ultimately enabling humanity to venture deeper into the solar system. The Moon is not just a relic of the past, it is a dynamic, evolving frontier that holds the key to our future in space. What further astonishing secrets, what revolutionary insights will the Moon's enigmatic far side unveil in the decades and centuries to come? The story of the hidden hemisphere is a testament to humanity's enduring spirit of exploration, a narrative that promises to captivate us for generations to come.
The Moon's far side, once a veiled enigma, has slowly but surely yielded its surprising secrets, forever reshaping our understanding of Earth's silent companion and, by extension, our place in the cosmos. We embarked on a cosmic journey, driven by pure human curiosity to uncover the hidden hemisphere, a world dramatically different from the familiar face we've gazed upon for millennia. We've traversed its ancient, heavily cratered highlands, explored the colossal South Pole Aitken Basin, and marveled at its unique geological history, distinct from the Maria-dominated nearside. We've discovered the tantalizing promise of water ice, a potential lifeline for future lunar outposts, and pondered the vast energy potential of helium-3, a resource that could one day power our world. We've witnessed the pioneering spirit of robotic missions, particularly China's Chang'e program, which dared to land on this uncharted territory, and imagined the profound scientific breakthroughs possible in the far side's unparalleled radio quiet zone. The Moon's hidden hemisphere is more than just a scientific curiosity. It is a crucible for humanity's future in space. It is a proving ground for the technologies and strategies required for sustained human presence beyond Earth, a stepping stone to Mars and beyond. The challenges are immense, from the engineering hurdles of resource extraction to the complexities of long-duration space habitation, but the rewards are even greater. The secrets unveiled on the far side are not just paradigm-shifting for lunar science. They hold the potential to redefine our cosmic destiny, to transform humanity into a truly multiplanetary species. Our quest to conquer the hidden hemisphere is a testament to our enduring spirit of adventure, our relentless pursuit of knowledge, and our profound connection to the universe. As we continue to push the boundaries of exploration, the Moon's far side will undoubtedly reveal even more astonishing truths, shaping our future in ways we can only begin to imagine. Join us in this grand adventure, unraveling the universe's profound mysteries. Subscribe to join us for more lunar adventures and cosmic explorations.